Okay, welcome back, everyone. Um, we are about to start module 1.6. My name is um, Joshua. I am a grad student in James Glacier's lab, and I'm gonna be talking about um, how to import uh, antimony models into CompuCell, how to execute them, and how to use plot windows to display simulation results. I'm gonna switch up really quick to share my whole screen. Do you guys see my screen now? Good. Okay. So what I'll be doing is I'll be walking through the presentation on the left side, and I also have NanoHub. I have the CompuCell version of NanoHub up and running in this right panel, and I would highly encourage you all to follow along as we build the model from scratch. So in this module, we're gonna cover how to use the threaded wizard to create CC3D simulations from scratch. We will talk about what are the minimal components that such simulation needs. We will talk about the structure of the CC3D project files, the CC3D ML and the Python Steppables. We will also talk about 20 code snippets, which are templates that allow CompuCell users to access convenient utilities from the CompuCell library. Then we will show how to import and load antimony models as freestanding models in CC3D. We'll talk about how the simulation steps between CompuCell and the ODE model need to be synchronized, and then how to access the values of the antimony model as CompuCell integrates it. And then we will plot these results. We will show how to create plot windows, how to add the data series, and then how to add data points into these data series. We'll have two exercises in this module. We will have one exercise and we will ask you to add additional data series. We'll walk you through how to add one or two, and then we'll ask you to add the remaining ones. And we will talk also about how to save data from the plot screen displayed by CompuCell. So this is just a quick reminder how to upload to NanoHub. We go to the Jupyter Notebook. In the Jupyter Notebook, we click we click File, and then we click Open. And then once we are in the home directory, we can upload our files, and this is going to be important. I'm going to explain it later. And once we have uploaded them in Jupyter Notebook, then we can access them through Threaded in the CompuCell tool. So I'll be talking. So the idea of this module, right, is and the next couple of modules is that we want to start from the ODE model, from the antimony model that James was walking you through in the past mod section, and we want to put it in the context of CompuCell, which means that we want to put it in a context in which we actually represent specific cells, spatially distributed, right? ODE models are very good. They're widely used to explore wide ranges of biological systems, and they can be very powerful tools when fitted to data, but they don't usually include heterogeneity between individuals, nor include any spatial resolution. And for some diseases, that stochasticity associated with individual agents and the spatial temporal dynamics are important predictors of the disease. And these images are examples of our attempts at cellularizing models of flu, and then this image shows the lung injuries in as flu progresses. And the idea is that the spatial temporal resolution of the infection can be actually used as a predictive tool for disease outcome. And we've been able to we've been able to specializing will be able to reproduce these spatial patterns. So what we've done for this particular set of modules is that we have uploaded a whole directory into the Google Drive, and the link is right here. What the idea is that we're gonna build the model from scratch, but each module is independent. We wanted each module to be as independent as possible from each other, although they build on previous modules. So we created different versions of the code, such that if you have problems in one module and your code at the end is still experiencing problems, we can continue into the following module by accessing the different versions. So for this particular version, we're gonna build the simulation that is contained in module 1.6 version 0. Okay, so now into CompuCell. So when we want to create a new simulation in CompuCell, we would usually start by using Wizard. Wizard is a code generator tool inside Tweeted. It provides a graphical interface, user interface that allows users to choose simulation properties and model components quite easily, and imports them into the project files. Full simulation, more complex simulations will require us to extensively edit the templates provided by Wizard, but Wizard is providing the templates that can be extended by users to include more complexity. So to launch Tweeted to launch Wizard, we need to first launch Tweeted. And right here, I am in player. So I'm gonna launch my Tweeted. And then once I'm in Tweeted, I can access just one second. This is happening on me. But I can access wizard by clicking in CC3D project, new project. And this is gonna open the wizard window for me, the wizard panel for me. It should look a little bit like this. It's a little bit zoomed in my browser. But in this first window, we just need to specify the file name and the specific directory where we want to create the project. There's also the option of choosing between the Python XML plus XML, in which case we will be able to specify model specifications both as Python scripts and XML. XML is a markup language, or just Python. We extensively prefer using Python plus XML. So we're gonna create a new simulation here. We're gonna call it Glaciers model. And then we can choose what is the location of that. What is the location of that file by clicking browse, and then we want to put it in our home directory. And it's going to create the glacier model. I'm going to call it 1 because I do have one already, so I'm just going to go ahead. Once we've specified the name, the project name and the directory, we can then we need to then configure the simulation properties. Here this window allows us to specify the simulation domain properties. Specifically allows us to to choose the lattice dimensions, and allows us to specify what the boundary conditions is, which means that allows us to specify what happens at the boundary of the simulation, and we will talk a little bit more about this later on. It also allows us to choose whether we want a squared lattice or a hexagonal lattice. We will use squared lattice for now. And these other concepts, membrane fluctuation, neighbor, or we can choose them from here, but we're gonna explain them later on. Finally, we can decide how long we want our simulation to run. We usually just put as much time as we can, and we stop the simulation as we run, especially when we are building exploratory models like this one. So for this particular simulation, we want our model to be to be 200. The length of this simulation domain is going to be 200 on the x-axis, 200 on the y-axis, and 2 in the z-axis. And if you guys remember from yesterday, from TJ's presentation, that was the basic structure of the framework that we use to simulate viral infection. And the reason we're doing this is because we want to have a layer of, we want to have a quasi 2D simulation domain where we have one layer where we can put our epithelial cells, and then we have another layer where we can put our immune cells and where the chemical fields are gonna later diffuse into. As for the boundary conditions, we want a periodic along X and Y, which means that whatever goes out on the X dimension comes out at the other end. Same with Y. And then we want no flux in the Z dimension, which means that cells cannot go up and down the z-axis. Our next option is to add cell. So here we can define the cell types. It's not gonna create cell for us, but it's gonna enable us to define cell types that can be attributed to cells once we create them in our simulation. So we are anticipating that for the next couple of modules, we are gonna need at least 4 different types of epithelial cells. The first type is gonna be the uninfected type. And we want those cells to be frozen. And by frozen, we mean that they do not move relative to each other. They are immobile. And then once we type the name and we choose whether we want to freeze the cell or not, then we can hit on add. The next cell type is gonna be the infected cell type. And as what it's gonna be frozen as well. Next type is virus releasing, and we're just gonna type it. We're not gonna create spaces in the we're not gonna create spaces in the cell names. So we're just gonna put it all together. These are also gonna be frozen. Let me ask a couple of questions really quick. When is the periodic boundary condition used? Well, the periodic boundary condition is used when you want your simulation domain to represent a small portion of a bigger, let's say of a bigger space. So in a sense, things can go through the borders of your simulation. When you have no flux, it's basically a box where everything in your simulation is contained inside of the domain. So once we have defined the different cell types that we want, we can hit next. In the chemical fields option, this would allow us to define any chemical fields that we want, but we're not gonna need chemical fields for now, so we're just gonna hit continue. The next window is the cell properties and behaviors window. Allow us to choose what behaviors we want our cells to have. Center of mass is usually is by default selected, but for this particular module, we do not need any cell properties because we're not planning on adding cells yet. So we're just gonna choose no cell properties, and we're gonna hit next. Once we do that, it takes us to the end of the wizard, and we can hit finish or done to complete creating the simulation. Once we do it, it opens automatically into it. So I did not pick any cell behaviors, and I actually, I now realize that I forgot to add dead cells when I was creating wizard. There is a way we can manually add them later. It's not gonna matter for now because we don't need cells per se for this model. But when you are in wizard, you want to add also this dead cells in the cell type specification. Good question, good catch. So now we have this newly created document, and we want to open the associated files, the files associated with the with the new CompuCell project. Just one second. So okay. So once we add it here, we can double click on this file under the CC3D simulation tab. We double click on the name of the project, and that is gonna open all the associated files in Threaded. So they're gonna be accessible for us. So asking a couple of questions. Yeah, we did not add any cell behavior. As I mentioned, we are not gonna add cells yet, so we don't have to specify them in Wizard. We can later add them manually using threaded code snippets that I'm gonna discuss a little bit later on. So we are not selecting chemical fields either, which we will add manually. So you don't have to choose any solver if you don't have, if you don't select any field. The solver is gonna be associated with the field, and we're gonna have a full module later on. We'll add later on. And now, Ching, yes, we will go over how to add manually. If you didn't add something on Wizard, we will add it manually. So, for example, in this case, I forgot to add the dead cells. That is something that we can manually add later on. Okay. So the first file that is associated with our project is what we call the main Python file. Or the main Python script. And this one, what it does is that it executes the CC3D classes and functions that we specify in and the steppables that we specified in another file called the Python steppable file. We very rarely edit this file because it updates if we want to add more complexity into our file structure. It usually updates itself as you add more and more complexity. So we rarely manipulate this file manually. The next file is the XML file. XML is a markup language where model specifications are organized in a tree structure, or more easily, they're just organized as categories. We do modify this XML file more often, but the important things about XML is that the properties that are defined here are static in the sense that they do not change throughout the simulation. We could do that as well, and we will show how to later, but in principle, the things that we define in the XML file are static. And if we look at what the content of that file right now, it does contain, for example, the dimensions of our simulation. It has this in this plot category, plots category. These were the dimensions that we chose and the boundary conditions that we chose. Note that no boundary condition was specified in the C dimension, and that is because the default is the no flux. And we also have the cell types that we chose to add in our in Wizard. We can see them here. It also includes this uniform initializer steppable that it's automatically gonna create cells, and we'll come back to it later. Right. So we could delete this. We're just gonna leave it for now. It's not doing any harm, but we're gonna delete it later when we're gonna create cells manually, because this does create cells automatically, and we might not necessarily want that from the get-go. Then the last file is the Python Steppable script. This is the file that we edit the most, because it allows us to specify and to manipulate model properties dynamically. This is where we define events and we change cell properties, and we, in general, change the properties of the simulation. It includes a default class called the Steppable class. And that one has an init function that is an initializer construct, is standard for class definitions in Python. Variables are going to be available inside the class. We will define in this section. It has a start function which execute routines that at the beginning of the simulation. Anything that we want to any event that we want happening at the beginning of the simulation, we will include in this section. And finally, it has the step function. Finally, next has the step function. This one is called every simulation step. And this is where we want to include routines that dynamically interact with the simulation and changes simulation properties. And finally, it has a finish function that it's called once a simulation is finished. So we do not need cells for this particular simulation, for this particular module. But I would encourage you to, after the module is over, to go back and revise and practice how to create cells using Wizard. Okay. So let's talk a little bit about so AJ, you could possibly download the file from the Google Drive. It's gonna be entirely updated. Let's talk a little bit about what the simulation units are in CompuCell when we execute a simulation. CompuCell simulations have two intrinsic units: the voxel and what is called the Monte Carlo stable. We just for short call them MCS. The voxel is the minimal spatial unit, and the simulation domain, what we call the lattice, is composed of arrays of these voxels. And then cells occupy some of these voxels. Chemical concentrations are defined in terms of the amount of chemical per voxel. And the dynamics of the simulation happens with cells change are determined in terms of what happens to this box inside these voxels. The MCS is the minimal time unit, and it consists on a series of attempts to change what's happening in each of these voxels, what types of objects occupy these voxels. So the question is, okay, CompuCell has this intrinsic unit, voxel and MCS, but how does these units relate to experimental units, to real world units, let's say seconds or micrometers? So the idea is that we can define these conversion factors at the beginning of our simulations, such that everything in the simulation is scaled or rescaled in terms of these conversion factors. So we usually use second to Monte Carlo steps as a conversion factor, but it could be days to Monte Carlo step, hours to Monte Carlo step, years to Monte Carlo step, although that one might not make a lot of sense. But you're free, the idea is that you're free to choose what the translation between the Monte Carlo step and the real world units are. For space, we can do multiple things. In this particular simulation, our spatial conversion unit is the cell diameter. So we're gonna define everything in terms of cell diameter. So voxels are defined in how many cell diameters are cells are defined in terms of how many cell diameters voxels they occupy, right? But usually you can also do length scales in terms of, let's say, micrometers to Monte Carlo steps, which would probably be the most sensible length conversion unit to use. And this is going to be important because when we integrate the ODE model, the one that James was showing earlier, with CompuCell, we need to define what the correspondence is between the units, the simulation units in CompuCell, and the time steps in the Antimony model. So if you guys remember, the units of the parameters in that ODE model were in terms of days. So we will have to specify how many days is each Monte Carlo step. And if you guys have questions about this, feel free to ask, and we can also discuss it further. So as I mentioned, a good practice is to start by defining these conversion factors in the upper part of our simulation. We're gonna first import useful libraries that we're gonna be using later on. But then we're gonna, as a good practice, we're gonna define what the conversion factors are at the top of our simulation. And we want what we're gonna do for this particular simulation is that we're gonna define one Monte Carlo step to be five minutes. And then since the units of the ODE model are in days, it's also convenient to specify the conversion between Monte Carlo steps and and days. So that's gonna be the translation from, just one second, maybe I can zoom. It's gonna keep going this way. And this is gonna be days to Monte Carlo steps. Next, we also want to specify the cell diameter, which means that we are specifying how many voxels each cell occupies at it, what is the width of a cell in our in terms of voxels. And this is important because this is what would allow us later on to define how many what is the actual length scale of the simulation, because depending on the cell size, we can then make the translation from voxels to length units such as micrometers, for example. So since we are assuming that our cells are going to be squares, we can say that the cell volume is going to be the cell diameter squared. These are the ones that we're gonna need for now. We're gonna have to specify what the relation between the antimony model and the MCS units are. So we're gonna say that the SBML step size okay, yeah, so good question. So we do use, good question. So we use cell volume as a property of how many voxels our cell occupies. When we're talking about, since we're creating a layer of cells, right? Then it's this cell volume, it's technically the area, right? But in this particular context, we use volume just to quantify how many voxels each cell occupies. That was a good question. So we want the step size to be such that my MCS corresponds to a particular number of days. Okay, and I think this is all we need for now. Okay, now to the fun part, right? So the idea is that now we want to add this antimony model that James walked us through in the previous model to CompuCell. Why do we want to do that? We want to do it because this is gonna serve the purpose of allowing us to check that when the right assumptions are incorporated into our simulation, the CompuCell simulation and the ODEs track exactly. So they reproduce the same results exactly. And by that, what I mean is if we erase any special considerations, CompuCell and Tellurium results should match perfectly with each other. And having the antimony model string in CC3D allows us to do that. That is just for the particular purpose of cellularizing a model. there's other reasons why you might want to include antimony model strings in CompuCell. You might want to do it to represent intracellular pathway signaling pathways that are specified in as ODE models. You might also want it to include it to represent whole organism rates. So, for example, if you are assuming that your simulation represents a part of or an organ, then you can attach these antimony models as representations of what's happening in the whole body. But again, for this particular simulation, we will be using this as a sanity check that our model is tracking the computer is tracking the tellurium model when the special considerations are not taken into account. So, and again, I'm sorry, to do that, I added a link to the text file that contains the antimony model. So the idea is that we can just copy that antimony model, and then we're gonna paste it just on the upper part of just below our conversion factors and before our Steppable class. It's not letting me paste from here. Let's see. I won't be able to import the code as I want it. And I cannot write the whole antimony string because it's kind of long. But the code is available there. What I'm gonna do is I'm gonna open the finished code here, so I can basically copy it from the finished code and paste it here. Because before this class, I went ahead and I uploaded all of the modules, which it would be a good idea for you. So I uploaded all of the modules already. So I have that code available. Just one second. Okay, so just one second while I get the code, the antimony string. The reason I had to do this is because it's not NanoHub is not letting me copy the antimony string from the code that I'm displaying in my computer into the file that I was working in. So I had to open the finished version of this model. Sorry. If you guys are experimenting the same problem, you can also do this, and yes, you can potentially upload the file via Jupyter and open it here as well. And you can do that by opening. By the way, let's try it, because that one is already, that's a good question, and that is already in this. It should be attached to, so you can, yes, you can do it. It's already attached in that. It's already included in the simulation that I uploaded. So you can basically copy it from there, but you will have to open it into Edit as well. And then now I can come back to the code that I was working at. And as I said, we're gonna paste it in after our conversion factors and before our Steppable class. Okay, I just wanna make sure that, because that was a little bit complicated, so I just wanna make sure that everyone is with me. Okay. So I'm gonna go ahead and close this one, this project, which I just opened for the purpose of copying the model. Okay. So the next step now is for us to, now once we have uploaded this file into the Antimony model, it should look a little bit like this. It should be below our conversion factors and before our Steppable class. And we can see that this is basically the code that James was working with. We added a little bit of, some content, but we will discuss that later. So no need to worry for now. So the simulation is in the Google link that was sent earlier. I think it was Giuliano. The important thing is that you will have to upload it using Jupyter. Okay, so let's talk now. The next step in the workflow, once we have uploaded the model string as a Antimony string, right? We have defined it as a string in Antimony as a Python string. We need to load this into CompuCell because as of now it's just a Python string. It's not doing anything. We normally do this in Tellurium by using the LOADA function. So we will have to get the equivalent of that loading function in CompuCell. Fortunately, Twedit has a wider range of code snippets that you can use that provide users with different sorts of templates to do different sort of things in the simulation. So for example, if we look at since we are in the Steppable file, the code snippets that will correspond to this file are provided in the CC3D Python tab in the toolbar. And it provides a lot of functionalities and templates to access utilities from the CompuCell function, from the CompuCell library. In the case of the XML file, it also has snippets to load different codes and to generate different types of codes in the XML file as well. The code snippets are usually going to provide a template type of script that we will need to modify to tailor to our specific simulation. So what we want to do is to load our antimony string into CompuCell. And we want specifically to load it as a free-floating antimony string. And what do we mean by free-floating? So what we mean is that we will have a copy of the antimony model loaded for the whole simulation. So it's not attached to any particular object in the simulation. It's attached to the simulation as a whole. It pretty much acts independently of what's happening in the model, unless we decide to establish some connection with it. But for the purpose of this module, what we're concerned with is that this module is going to be loaded as a free-floating model, which means that it's not attached to any particular object in the simulation. So it's sort of like freestanding. To do that, we will come to our start function. And in our start function, we are gonna, the start function already comes with a comment that explains when the function is called. It says any code in this start function runs before MCS = 1, which means before the first simulation step. We can delete the comment. It's just for informative purposes. Now, what we want is we want to use the Python, the CC3D Python code snippets from Twitter to be able to load this antimony model. And when we click on CC3D Python, among all of the options that we have available to us, there is this SBML solver option. And this would allow us to define not just antimony models, but in general, models described in some sort of standard shareable language, which could be SBML or for SBML or CellML. So I had a good question. The question was whether you would use a non-free floating antimony string for something like cell differentiation. The answer is yes, because in that case, you want to attach the antimony model to a particular object, let's say a cell, and then that model attached to the cell is gonna determine the cell properties, and based on those cell properties, then you can later on decide what's going to happen to a cell. It can be differentiation, it can be cell death, and so on and so on. Yes, we will work on it possibly tomorrow. So what we want is we want to add a free floating antimony model. and we will, we get that option here. So once we do that, we get this this is an example of a snippet code that shows a template, code for us to use and adapt depending on what we want to do. Okay. So you guys can see that it has a lot of options for us. Specifically, it allows us to load a model from a file. In this case, we define it as a string in our Steppable script, but we could also upload it from a file. Let's say from the text file that I added. We can also define it from the string itself, and we can specify what initial conditions for the model are. What we're gonna do is we're gonna modify this inputs with this template inputs, so we can actually load the Antimony string that we had in our simulation that we are adding in the Python script. So the first thing is we're not adding it as a file, so we're gonna get rid of that option. We're not gonna change the initial conditions of the model. We're gonna let the model has the initial conditions that are established inside the model. But we do want to modify the model string to be able to reference the string of the Antimony model that we loaded. And the string name, the variable that we attach that Antimony model to, what's called, I'm sorry, I'm used to using my shortcuts in my computer, but I cannot use them in NanoHub. So this is the variable that we use to load our Antimony model. What we're gonna do is we're gonna copy that variable name and we're gonna paste it here. Model name is a reference to the Antimony model, and we will extensively use this reference later on when we want to access the number of the name of the SVM, the values of the SVML model. Okay, so what I'm gonna do is I'm gonna finish defining this, and then I'm gonna take a moment to let people catch up and ask questions if they're having specific problems. What we're gonna do is that we're gonna define the model name. We're gonna call it ODE model. No, we are renaming the model. So instead of the template option that we had, we're just gonna rename it ODE model, so that we can access the values of the Antimony model later on. And here, this one is particularly important because here is where we tied up the simulation steps in CompuCell with the simulation steps in the model. And that's why we define a variable called SVML step size among our conversion factors. So we want to use that one. as the step size to integrate this model. And I will explain, just in a little bit what this is doing. Okay, so let's just pause for a second to make sure that that people are able to follow through. So I see I see that the main problem is not being able to paste the antimony string in NanoHub. That was kind of unexpected. But the way we solved it is you can upload the text file to NanoHub using Jupyter, and then you can open that file by clicking open in Twitter, and then you open it and it will show up as a text document. Yes, adding the antimony model. So what I used a snippet option, a code snippet option. I went to CC3D Python that gives me many many options to access templates. The one I am interested in is the SBML solver. SBML is a standard shareable language for biological models. We use it generally to refer to any any standard format to share models, antimony strings being one of them. And then we go to add antimony model, add free floating antimony model. And then we click on that, we get a template code snippet. We have to do it inside the start function. And then we change the options, the inputs to tailor it to our particular model. In this case, the antimony string was defined as ODE __ model _ string. The model name was defined as ODE. This one we're going to define ourselves, and it's going to be for later accessing values in the model. So this is going to be extensively used. I recommend using a simple but unique name, so you can access it uniquely, but also relatively easily. And then we set the step size of the model to be what we define in our conversion factors. Okay. So I do not see poll results, so I'm not sure where people stand at the moment. Okay, just giving a couple of minutes for people to catch up. So once you upload the text file to Jupyter, you have to make sure that it's uploaded. And then you click open here and thread it, and you should be able to access it. If you uploaded the whole directory as well, you can access it inside of it as well. And when I open it, I have it available as a text file among the files that I have open into it. And I can copy and paste it from here. Okay, let's continue so we can start using this antimony string in CompuCell now. So we adapted the antimony string options to reference this particular model that we are importing into CompuCell. Now we can actually run CompuCell. We can actually run this simulation. Open simulation file. We go to player. We go to open simulation file. We go through NanoHub. We go to our home directory. We open the corresponding project that we were working on. And we should be able to launch the simulation. As I mentioned before, we left the blob initializer on, which means that some cells are going to be created automatically in our cell domain, and those are randomly. They are placed in a square in a box, but they are randomly chosen. We won't care about that right now. If we hit play, we see that the simulation is stepping through, right? But we are not seeing any outputs. You could also, I'm not exactly sure how it works in I'm sorry, we loaded the model, but we haven't time stepped it. You can also play, you can also, at least if you're running locally, you could potentially run the simulation from by clicking in the Python icon, in the player icon up here. That would start CC3D and launch the simulation. So when I launched it, everything the simulation did was just to load the antimony string. So it's not doing anything to it. So what we want to do next is we want CompuCell to integrate this model. So to do that, we need to time step the antimony model in CompuCell. And CompuCell has a convenient function called timestep_SBML that integrates any SBML and antimony model forward in time by the unit specified when the step size was defined. This function is typically called once per Monte Carlo step. So that is the reason we need to specify how much time in model units, which in this case is days, is the Monte Carlo steps. Okay, so to include this function, we need to do it in the step function, right? Because it's gonna be called every Monte Carlo step, and the step function has already a template that it's been executed, but we want to modify it to include our time stepping function. And as I mentioned earlier, this time stepping these functions are conveniently located in the threaded tab that generates the code snippets. We go to SBML solver, and then we have this option called time step SBML model. We click on it, and it automatically generates this SBML function. We need to define it outside of the comments. If anything, it's good practice just to delete what the original comments were, what the template comments were, and then we include this timestamp SBML function. Okay, and just remember that this one goes in the step function because it means that the model is being integrated every time at every simulation step. And we're gonna comment that this is integrating model. Okay, now we can save the simulation, and if we go back to player and we play the model and we re-execute the simulation, now the simulation is running. Now is time stepping or integrating the model, but I haven't established any way of outputting what the results of integrating the ODE model are. So that is what we will be doing next. To do that, we need to be able to access the values of the Antimony model as it's being integrated by CompuCell. And the way CompuCell stores the Antimony model and its values, its current state, is as a Python dictionary. And Python dictionaries are unordered collections of items of objects. Each object has an associated key or a name and a value associated with that key. So to access the values of the Antimony model, we will need to reference their keys. And their keys are gonna be the different variables of the model, specifying in the Antimony string, or the parameter values, or the rate equations. So the standard way of accessing the value inside a dictionary is to have the dictionary name, the brackets, the name, and the name of the key as a string in quotations. And the reason we need to access this Antimony values is because we want to be able to display them somehow. So once we integrate the model, then we can access what these values are. And to do that, we can again use the threaded code snippets options. We go again to SBML solver. And in this particular case, we go to get SPML value from free floating model. And I'm gonna stop here just to give everyone a little bit of time to catch up. So let's see, in the meantime, whether I can answer some questions. Okay, good. So again, we are gonna retrieve or reference the values of the different variables of the ODE model as they are being integrated by CompuCell. Okay, so once we click on that code snippet, then we get another template. And the template, I'm sorry, I clicked on the wrong snippet. SPML solver. Get SPML value for free floating model. There. Okay, let's try to see whether I can answer some questions. Yes, I did added the name of the string that I did use to define the antimony model. The antimony string was ODE underscore, and I'm gonna type in ODE underscore model string. The reason, Josh, the reason you were not able to see any cell borders is because of the domain you were adding the cell in the cell domain. Okay. So I don't. Oh, I'm sorry. Right. Okay. So now, now that we have access to this code snippet, we can actually reference the different values of the model. And the way we're going to reference the values of the model is by using the name of the variables and the parameters and the rate equations defined in the ODE, in the antimony string. So for example, we know that in that model, T corresponds to the number of uninfected cells. The snippet I used was CC3D Python, SBML solver, and get value of free floating antimony string or SBML model. So as I was mentioning, T is the number of uninfected cells in the ODE model. Now we have to specify also what the model name is. And that's what I was referring to when I mentioned that the name that we give to the antimony model is the name that we're gonna extensively use later on to reference the values of this model. So I need to change this to be ODE model. It has to be the exact same name with caps and everything. Right. So one of the things that we can do now to see whether the CompuCell is actually integrating the values of this model is that we can print the values at each time step to the console. The Python function print, it outputs messages to the standard output display console. And CompuCell has its own integrated console where information about the simulation is being displayed. It's usually, sometimes it's basic information about the simulation. So for example, what step the simulation is at. But it can also include error messages, and it can also include anything that I am able to print, that I indicate to print in my Steppables script. So now I'm printing the value of the number of uninfected cells in the simulation as CompuCell integrates the antimony model. And if I execute the model again, I need to save it. And if I execute the model again, I have to stop and relaunch. Oh, it's not printing anything. Let's make sure that everything is correct here. And I'm not exactly sure why it's not outputted to the console. Are other people experiencing the same problem? So I'm not sure I'm not sure if it has something to do with NanoHub and the console. Not exactly sure. Okay, so yeah. So yeah, as TJ is mentioning, so it's not printing for anyone in Okay, so it seems to be a little bug right now. So the whole purpose of this was to show that the that we could output to the console, but seems that we're having troubles with that. So we're just gonna move on with the next part. But in theory, this is how we include, how we decide that we want to include stuff into our simulation, and it should print in the terminal or the console. So. But the basic idea was that that this code snippet allows us to access the values of the SBML model as it's been integrated in CompuCell. So this is the specific reference, right? If I wanted to reference other variables, I would reference them by the name of, by their specific names in the Antimony model. Let's say I want to access the number of infected cells, or I1 cell, what it's called I1 cells in the model. I would do it this way. And if I wanted to access, let's say, a parameter value instead of a variable, I would do it as well. I would use exactly the same syntax. Let's say P, right? Which is one of the parameters of our model. Another parameter is T0. And the whole purpose of this was basically to show how to access parameters and values of the SBML model as we integrate it. It's sort of like the fact that we couldn't print into the console sort of like give us motivation to do the next part, which is creating plots. So we want to be able to use use these values from the SBML model to create plots that shows the evolution of the ODE system in time. CC3D has extensive capabilities to display time series as scalar quantities, and also to build histograms. This image is an example of the many different types of plots that you can create using CompuCell. So the idea is that the same way m.plot works in Tellurium, we can also generate plot windows in CompuCell. And at the end of this module, we will compare how the modules of how the plots of CompuCell compared to the plots generated by Tellurium. CompuCell has built-in functions, but we will need, as we've been doing consistently with these code snippets, we will have to modify them for our specific needs. So as I mentioned, the purpose is that we want to be able to visualize the results of time step in the ODE models, so that we can compare the results of Tellurium to the results of CompuCell. And we will later use that to compare the results of our cellularized version, not just the Antimony model, to the ODE models as well. So creating plots using Tweeted follows a quite simple workflow, and this is important because we're going to be doing it repeatedly. for the next for the next couple of modules. So I do want you guys to follow along with me. So the workflow is that we will first create a plot window in the inside the Steppable class in the start function, right? As we said, we want in the start function, we want to include codes that are gonna happen at the beginning of each simulation. And we want at the beginning of the simulation to open the plot windows. Then we need to define what data series are associated with that plot window. And we will that also in the start function. And then later on in the step function, we're gonna add data points to each data series such that they are displayed in the plots. Let's see what's right. So again, as I've been showing consistently, there is the code snippets in Threaded support creating, give users many different options to create scientific plots, either in the form of time series or in the form of histograms. So the first thing we're gonna do, as I mentioned, is that we're gonna add a plot window. Just for good practice, we're gonna define the name of the plot window in our init function such that that name is available across the Steppable class. But we're not gonna give it any particular, we're not gonna attribute any object to it. It's just making it available to the class. Next, we will use the templates to generate the plot, the window plot, the plot window. So to do that, we go to CC3D Python, scientific plots, and we have three options. As I meant, we have three options: the set of the data point and to add data points. We don't refresh plots. We generally do not use refreshing plots. The first thing we're gonna do is that we're gonna set up our plot window. When we click on that option, it generates a boilerplate code snippet code that allows us to, that creates a specific plot window. But as I mentioned before, we need to tailor this plot window to our specific needs. The plot window, it's always, when you click on that code snippet, it's always gonna generate the same boilerplate. So you're always gonna need to modify it. This first line attributes the plot window to this handle. And then specify plot options such as the title, the axis titles, the scale of the axis, and grids. So the important thing about this handle is that it has to be unique for each plot. And this is a mistake that I actually run into often because of not being too careful. So this handle needs to be unique for each plot window that we create. And that is the reason, that's why we have defined the name for the plot window in the init function. Also, it has to have a unique title, not just a unique handle, but also a unique title. So what we're gonna do in this case, I'm sorry. There's also options to modify some of the inputs of the plot window. So for example, we could change the name of the x-axis, the y-axis, whether we want our x-axis to be linear or a logarithmic scale. Same with the y-axis, whether we want our grids on or not. And there's also other functions like we can set up legends. And for specific options, you can actually access the PyQt graph documentation. And we will generate a series of different plots. So as I mentioned, we created the name of the plot, the handle of the plot in the init function. Now we have to modify the inputs in our plot window to make it to tailor it for our specific needs. The first thing we're gonna do is that we're gonna change the handle of the plot window. So the handle of the plot window is gonna be the same as I defined in the init function. I'm gonna use this plot to plot my cell population, my population of cells. So I'm gonna call it population data, as that's gonna be the title of this plot. In the x-axis, I'm gonna define it in terms of time, and specifically, because I'm gonna rescale, because I have that conversion factor, I can convert between compute cell units, the Monte Carlo steps, and model units, which are days. So I'm gonna plot this in days, but I have to keep this in mind because when I add the data points, I'll have to make sure that I convert my Monte Carlo steps to days. In the y-axis, it's gonna be the number of cells. And I want for this particular plot, I want my x scale and y scale to be linear. I'm gonna turn on my grid, and I'm gonna set up my my legend. And this one is not available in the cuts, in the snippets, in Threaded. This one is one that you can reference in the PyQt documentation. But the specific syntax to turn on my legend is this. Good. Okay. Now I have created the plot window. And tailor it to the specific data sets that I'm going to be plotting. So it should look something like this. The next thing I'm going to do is that I'm actually going to add data series to this plot window. This is not adding data itself, it's just adding a placeholder so I can reference it when adding data later on. It's important to know that it has to be the same handle as the plot window, otherwise you might be plotting it in a different plot, which again is something that I often do if I am not being too careful, especially when creating multiple plot windows. So we need the same handle. The standard code creates, when you hit on when you use the code snippet to generate the plot window in the start function, it's always gonna include these two standard data series, and these are the ones that we're gonna modify. It allows us to define what the name of the data series is, and this is gonna be important because this is what I'm gonna reference later on to add data points to this data series. Whether I want to display this as lines or dots, again, there's other options available in the PyQt documentation. What color I want to associate with this particular data series, and the size of the marker in this data series. So yeah, the original snippet has its standard, but we're gonna modify it. So we want to, the first data series that we're gonna include is the uninfected cells data series. And we're gonna call it uninfected ODE because it refers to the number of uninfected cells in the in the SBML model. I'm gonna change the color to blue just for convenience. And then the size of the marker, I can just define it here, but since we're gonna create multiple data series, I'm just gonna go ahead and define it outside. I'm gonna create a variable called line size and set the value of this line size to be 3. And for the moment, I don't need any other data series, so I can delete the one pasted by the standard snippet. Okay, so this should create a plot window already in CompuCell. So if we go to CompuCell and execute CompuCell again, syntax error. So here's where you guys can see errors in the code. So I'm sorry. It's not equal is dots. Again, this is from PyQt documentation. And we can come back and execute CompuCell. And it's gonna create a plot window called population data that has the number of cells on the y-axis, the time in the x-axis, and it has one data series associated with it, which is called uninfected ODEs. And I'm gonna give a little bit of time for people to catch up with me. So what I'm gonna do, because the next, we're gonna add the data series, and then we're gonna have an exercise where we're gonna ask you to add the remaining variable cell population into the into this same plot window. And then what we'll do is we can pause at the exercise to give people a chance to grab lunch and work on the exercise as they launch. Okay, so now we go back to CompuCell to edit. I'm sorry. And I mentioned that there is three steps in the workflow to generate a plot window. We generate the plot window with this add new plot window method. We add data series with this .add underscore plot, and now we need to add the data series itself, the data points itself. Those we're gonna add in the step function, because we wanna see how this quantities are changing as the simulation progresses. We can come after integrating the model. We can use the CC3D Python scripts, scientific plots, and now we have the option to add data points, and it specifies that it has to be in the step function. Okay, when we click on that snippet, it generates two template codes as to how to generate how to add data to the window, to the data series. Again, we need to modify them to our specific needs. Here you can see the references to the data series, so I need to make those two match. Here is what I want to plot in the x-axis, and then here is what I want to plot in the y-axis. Okay, so what we're gonna do for this exercise is that before the break is we're gonna plot the number of uninfected cells in the original ODE model. Okay, so we need to modify the provided snippet first by using the correct handle, which in this case is pop data when add data plot window is provided, and now we need to reference the specific data series that I'm going to be adding this data point to. Now, this is what I'm going to be providing what I'm going to be plotting on the x-axis. And as I said before, we're going to be plotting the values of the model. The model is specified, the intrinsic units of the Antimony model are days, so we need to convert back from the CompuCell unit to the model unit, which is days, and that's why I had that convenient conversion factor that I define on the upper part of the simulation. And then what I want to plot in the y-axis is the number of uninfected cells, which I can reference here using this code. And I paste it. And now I can save, and I added the the data points to my uninfected ODE data series. Now, when I come to CompuCell and I execute the simulation again, I can see now how the number of uninfected cells is changing as CompuCell integrates the model. I walked you through all of this, but this is good for you to have in the slides. And you guys can see that it's happening in the scale that I defined in the x-axis in terms of days. I'm gonna pause it for a second. So by day 1.5, all of the cells on the antimony string are already infected. And when I compare to the OD model generated by Tellurium, those match exactly, which is what I expect to happen if I am integrating the model correctly. Okay, so what we're gonna do is we're gonna pause here and we're gonna give people a chance to work on this exercise. The idea is that you now need to add the remaining series to data series and data plots to the plot window, so we can see all of the cells in the population data window. So, James, do you want to give time for lunch? Okay. Yes, we're gonna take a break for lunch now. If you guys can work in this exercise as you have lunch, it shouldn't be too complicated. Then we'll catch up after lunch. We will resume at 3:15. Hello, everyone. It's 3:15, so we're gonna be resuming here shortly. I just wanted to send a poll out there to um, to see how many people were able to work on the exercise, and if you had any questions related to it, any problems. Um, as I mentioned at the beginning of the presentation, uh, the full version of the code associated with this module is going to be available. So even if you're unable to complete it at this time, for future modules, we will start with the versions that we are providing, so you can um, continue working on constructing the code, and then come back later at your own pace and add and review the exercises. Um, let me just go back to sharing my screen. Okay, so the exercise consisted in generating plots for the remaining data series. And by the remaining data series, we meant the number of infected cells in the ODE, the number which corresponds to the I1, the number of virus releasing ODE in the ODE, which corresponds to the I2, the number of dead cells in the ODE that corresponds to D, the number of effector T cells in the tissue that corresponds to E, and the number of effector T cells in the lymph node that corresponds to EL. So I went ahead and follow the workflow, generated different data series that are associated with the population data window, define the name of the data series that I'm going to be associated, and I set up the remaining settings manually. So I chose colors, different colors for each data series, and I chose them all to plot them as lines, because later on that's going to be important for our comparisons. And I use the same line size for each of them. That's why I chose at the beginning to define that outside of the specification of the data series. That was all in the start function. In the step function, then I added the data points by by first using the handle to the window, which is population data window. Then also referencing each of the data series that I was referring to, using the same conversion factor for my time units. And then what I did was that I defined the number of the variables of the Antimony model as independent variables. And I kept, I initialized new variables that then I passed into the plot windows for the number of cells uninfected, the number of cells infected, the number of cells virus releasing, the number of dead cells and immune cells. So this walks you through the whole process. So now we can go back and re-execute CompuCell. So now the population window should include all of the populations that I included in my all of the data series that I included in the code. And I can see as CompuCell is integrating in time the model, how the cells are, the number of uninfected cells is going down as the number of infected Python releases is going up under dead cells. And when we compare that to the results generated by Tellurium, we see that we get the exact same curves, which means that we are integrating the model in the correct way. So for the remaining of this module, what we're gonna do is we have added the immune cells. We have added all of the epithelial all of the cells in our model, but we still haven't added the virus or the cytokines or the APCs in the lymph node. So this is what we're gonna do is that we're gonna walk up again through the same workflow, this time adding a plot window so we can add the remaining pieces of data that we haven't included yet. So, and this is just because we're gonna keep doing, plots are very important and we're gonna be working with them extensively. So we wanted to go over the same process twice so we get an idea, we get a sense of what the workflow should look like. So as I mentioned earlier, just for good practice, we're gonna define the handle for the plot window in our init function. Just 1 second. We're gonna call this plot window, we're gonna call it MED for medium, diff for diffusive species, data window. We initialize it to nothing. It's just a matter of initializing the handle. Okay. So once we have added the plot window, we have added the we have initialized the plot handle. Again, we come back to the CC3D Python pull down menu, and then we access scientific plots, and we choose the setup because we're gonna set up a different plot window. And then again, this should be familiar because this is the same template that showed up the previous time. So this time we're gonna change again the specifications so it's tailored to our specific simulation. The first one is the handle that I've defined. I need to change also, as if you guys remember the title cannot be the same as the previous one. What I'm gonna do for this one in particular is that I'm gonna call it total diffusive species. The time is gonna be in the same units, which is the model units are days. The y-axis in this case is gonna be the amount of diffusion species. Our x-axis is gonna be linear, but in this case, if we remember how the vital load curve is plotted and how we were plotting the cytokine curves, they were plotted in a semi-log axis. So the y-axis was in log scale. So we now need to specify that our y scale, it's gonna be logarithmic. Again, we want to turn on our grid, and we want our legend so we can identify easily which data series is which. And as I mentioned previously, this comes from the PyQt documentation. Okay. So now I have created this second plot window. Now the next step in the workflow is to add the different data series, and I have three data series that I have to add to this one. I have to add the virus. I have to add the cytokine, and I have to add what we've been calling the APCs, or the lymph node cytokine. So we're going to name this the first series. First, again, always rename the handle. We're gonna call this one medium vital ODE, or med vital ODE, med for medium. Same style. All of the data series associated with the ODE we're gonna plot as lines. And then we're gonna use the same line size as the previous. Okay. So instead of modifying the whole, instead of modifying the second one, I'm just gonna copy the same snippet. I'm gonna paste it below. Have to make sure that the indentation is correct, and I'm gonna call this one med CYT for cytokine local ODE. And then the color for this one is gonna be blue. You guys can see that once you have a piece of code that corresponds to what your simulation requires, it becomes much faster to generate the code. The last one is gonna be called med site for cytokine, lymph for lymph node, ODE. Same configurations, except that this time it's gonna be green. Okay. And then that was the second step in the workflow. The last step will be to add these data series. So first, I will need to reference the values of the SBML model. V corresponds to the virus. C corresponds to the cytokine. And CL corresponds to lymph node APCs. We're gonna define them as, one important thing about this is that when I add the data points, since I am plotting on a log scale, these values need to be greater than 0. So we're gonna have to add a if statement such that the data points are added only when the values of this when the values on the ODE model are greater than 0. So to do that, again, I can copy this. Well, let's just walk through the process so you guys get familiarity with the pull down menus. I can come down to CC3D Python, go to scientific plots, and add data points. Okay, and need to use the proper handle for the window. Need to have the right reference. It's gonna be virus. Need to rescale my time, my y-axis. And then I would need to define the variable corresponding to the value of the antimony model before using it in the to add the data series. Now I can use that one. Then I can use the same snippet as I did before to add the remaining data points to the data series. And then we're going to define 2 new variables to get the values from the ODEs. from the antimony model. And then now I can reference this. These new variables that I create and it's inside the data sets. So if I didn't do any mistakes in referencing the data cities or initializing the variables, it should be good to go. When I launch CompuCell again, yeah, I did have a syntax error. I'll just correct it right away. But we can see now, wait, I think my CompuCell crashed. But that was actually the last version. I'll relaunch it. That was the last version of the code. But what happens is when you get the correct syntax, then you can actually see the plots of the total diffusion species in terms of the vitals, the cytokine, and the lymph node APCs. And when we compare them to the results from tellurium, they match closely, which means that we have generated the right code. And that version of the code is available. The version that generates all up to here is a version that you guys can download for it's the version that you guys can download from the Google Drive. That is the end of this module. I just want to give a chance to for people to ask questions to make sure that people have caught up with the exercises and at least understand the workflow of generating plots in CompuCell. Let me see if I launch it now. Right, I get the error. I can open projects by, I can reopen my project by, and this is what I was explaining in terms of the console window displaying error messages. We can trace back where the error is, and the error seems to be that I define day instead of days. Let's save the simulation. I can. And I made another syntax error. Those are pretty common if when we're dealing with multiple variables. In any case, any questions that can be addressed at the moment, even if you haven't finished anything that was not clear in terms of what the workflow is and where to access the specific, where to access the snippets of the code, because that's the most important thing, that you guys are able to access the code snippets so you can generate the plots yourself. Yes, the videos are available and will be available. Okay, you guys can see now that it's running. I corrected the syntax errors that I had. It's not plotting anything yet because the values are not greater than 0. Wait, there has to be some effort because they should. Oh yeah, so I need to add the conditions, but you guys can follow. You guys can, when we launch the whole, if you guys upload the code as provided in the code provided in this version should be the final version without errors. I can close that now on this one, which was the one we were using just to generate the plot from scratch, the simulation from scratch. And now I can launch this one, CompuCell. Oh yeah, CompuCell crashed because of the error that I. Okay, so so if there's no further questions, then I'm gonna move on to the next module. I'm gonna need just a couple of minutes to set up all of the presentations and the simulations. So it's gonna be 5 minutes to generate to put up all the information that you guys can see it running now. This is the version provided without syntax error, so you guys can see the diffuse species. Okay. Yes, good question, because it's actually in the next slides. I actually forgot. There is an option to save these plots as different outputs. If I right click on them, I can, if I right click on a plot, I get this pull down menu, and I hit, and I can export them, and it's gonna give me the option of exporting them as image files, as SVG files, as matplotlib windows, or as SCV plot tables. So we usually use these SCV plots to export the data from the plots, but you can also save it as an image or download the matplot window, the matplotlib window if you want to re-execute it in Python. Once you hit export, once you have an option and hit export, it will open the play. It's gonna ask you the specific place where you want to save, and you can add. Why do I check if med vital total is greater than 0 before adding the data? Because the plot that I am using, we set it up to be in the log scale, and log scale does not support 0. So it would actually throw an error. It would throw an error and computer crash. So we have to set up the conditions such that the data it's added all the plot to the plot only when the values are non-zero or greater than 0. Right. We can also fix scales. We can and we can play with some of that stuff. But I do want to get into the next module. Can we start the same seed every time to get the same simulation from the beginning? Good question. So, right, TJ is answering the question. You can, but for this particular simulation, it's really not it doesn't really matter, because we are not using any. So far, we haven't used any of the capabilities of CompuCell in terms of the cellular aspects of it. So we're just integrating the model, and that is going to be entirely deterministic. Okay. Yeah, that was the end of this one. Good. So just 1 second, I'm gonna just I'm gonna set up my next module, and I'm gonna start reshading in